Hello everyone, welcome to all of you in my lecture today. So today I'm going to discuss the heterogeneous catalytic reaction system, in which I will be talking about various rates that will be used in representing the rates of the reactions in case of heterogeneous reaction system. So before going to the rates, I'll be talking about what is the basic difference between the homogeneous reaction system and heterogeneous reaction system, because we should know about the difference between homogeneous and heterogeneous reaction system. So if I'm talking about homogeneous reaction system, so what happens? I won't be writing the definition, but in case of homogeneous reaction system, what you will see, the reactant and product and the catalyst will always be, this will be always available for the reaction, right? So if we talk about the homogeneous reaction system, so in a homogeneous reaction system, what happens? The reactant, product, and catalyst always be available. Or you can say that reactant will always be available for the reaction. But in case of heterogeneous catalytic reaction system, what happens? Just tell you. Let's understand. In case of heterogeneous reaction system, what happens? If there is a catalyst over here, let's say here, if there is a catalyst, right? So in this, and obviously the catalyst will be solid. I'm talking about the solid catalyst. So if reactant over here is in the bulk phase, let's say if your reactant is a, so this reactant has to diffuse from bulk phase to the surface of the catalyst, right? So let's say here the reactant will come and it will get diffused into the core of the catalyst. So first it has to reach the catalytic surface, right? So here what you will see, the reactant will always, reactant is not always available for the reaction. So once the reactant will, diffuse and it will reach to the surface of the catalyst, then only the reaction will take place and the product will get formed. But in case of homogeneous reaction system, what will happen? The system used to be in the homogeneous mixture condition, means your reactant and the catalyst will be in the homogeneous condition in the same phase. So what happens? Whenever the reactant will be there, the catalyst will always be available for in the vicinity of the reactant, and the reaction will take place and the product will form. So this is the major difference between the homogeneous and heterogeneous reaction system, right? So when we talk about gas solid catalytic reaction system, so we'll be defining the rate of the reactions, right? So since in case of homogeneous reaction system, if you can recall, for homogeneous reaction system, so for homogeneous reaction system, let's say if a reactant A is getting converted to product B, so there I have defined that the rate of reaction in terms of A, that is equals to -1 upon V, and that was your dNA by dt, right? So dNA by dt. So this was your rate of reaction in case of homogeneous catalytic reaction system, right? But when we talk about heterogeneous catalytic reaction system, various rate has been defined for the heterogeneous catalytic reaction system, and based on that we will calculate the reaction rate and the parameters that will be asked in the question. So first I'll be talking about the rate of reaction on the basis of unit mass of solid. Rate of reaction on the basis of unit mass of solid, right? So generally I'll be denoting it as minus of RA dash, right? So obviously reaction I'm talking about, your reactant A is there, so that's why I'm writing in terms of A. So that is equals to -1 upon W, and obviously your dNA by dt. So in this condition, what is happening over here? Only the volume is get replaced by the weight, right? That's it. So let's say if they are asking you to calculate the moles per kg per second, right? So rate in terms of moles per kg per second. So if you'll see GATE question, GATE has asked this kind of question on GATE 2020 or 21. I don't remember exactly, but yes, in this year, GATE has asked a question on the basis of calculate the rate of reaction on the basis of weight, that is mole per kg per second, if the rate of reaction in terms of mole per liter per second was given. So you can convert something like that in that way. So you should understand these things, how you can convert this reaction. Now, second, that based on the unit interfacial surface area, based on unit interfacial surface area. So generally it occurs in two fluid system, right? So here it will be denoted as minus of Ra double dash, that is equals to 1 upon Ss, and obviously dNA by dt. So now here what happens, your volume is getting replaced by Ss, that is your surface area of the catalyst. So here you can see Ss is your surface area of solid, right? And obviously the third one is that is based on unit volume of solid. So this is mostly, I mean, this kind of things will happen mostly in gas solid catalytic reaction system. Gas solid catalytic reaction system. So generally you don't have to remember where it will be used, but you have to understand how the mathematics work over here. So that can be written as minus of Ra, that is 1 upon V of solid, and obviously dNA by dt, right? So this is how the reactions can be written in terms of various, in terms of per unit weight, in terms of per unit surface area, in terms of per unit volume, right? So this was the basic things about the heterogeneous catalytic reaction system. Now I'll be moving towards the, just wait one second, I'll have to enter page. Yeah. So now I'll be moving towards the gas solid catalytic reaction system, how it will happen, and how you can calculate the interfacial, rate of reaction on the surface of the catalyst. Because I have told you that reactant has to diffuse from the bulk phase to the solid surface of the catalyst, I mean surface of the catalyst. So obviously there will be interfacial rate of reaction you should know, and after that how the reaction will take place, we will get to know. So gas solid catalytic reaction system. So what happens here? So here, let's say if there is a catalyst, right? There will be a solid catalyst, right? So what happens? Reactant over here is in the bulk phase, right? So here in the bulk phase, let's say it is in the gaseous phase. So the reactant, the concentration of reactant in the gas phase, which is in the bulk, is CAG. And now what happens? This reactant has to diffuse from this bulk phase to the surface of the catalyst. So here I am assuming the interfacial surface area, that is the concentration of reactant at the interface, is CAI, right? So what happens? And let's say this is a non-porous solid. So if the solid is non-porous, then what happens? The reactant will not diffuse into the solid. I mean, in further discussion, I'll be talking about the porous solid. But right now, I'm just talking about the non-porous solid, where the reaction will take place on the surface of the catalyst only. So how this kind of reaction takes place? So just try to understand one thing. What is happening over here? First, reactant is getting diffused from bulk phase. Here, it will be your bulk phase of the reactant, which is in the gaseous phase, right? Gas phase. So reactant is getting diffused. So here, what happens? Your mass transfer is taking place. Mass transfer is taking place, and the mechanism of mass transfer is convection, right? So if you recall the concept of mass transfer of convection, then you can write that, let's say mass transfer coefficient here is Km. So what is the rate of mass transfer? So I can write rate of mass transfer, that is equals to obviously Km into Caz minus Ci, right? So this one is rate of mass transfer. Now, what happens? This reactant will come on the surface of the catalyst. Now, reaction has to happen on the surface of the catalyst. So what you can write? That is rate of reaction on the surface of catalyst, that is equals to Kr. Let's say I'm assuming the rate of reaction is, Kr, and obviously Ci. So your Km is your mass transfer coefficient, and obviously Kr is your rate constant. And obviously, I'm assuming the rate of reaction which is happening at the surface of the catalyst is your first order, right? For the simplification of the mathematics over here. So what happens here? You can see their mass transfer is taking place and the reaction is happening, right? So this flux is kind of, you can see the analogous. This one is analogous to heat transfer or mass transfer kind of thing. So here, what happens? Mass transfer is taking place, and here there is a reaction. So what happens? Rate of mass transfer, that is equals to rate of reaction. If I am talking about at steady state. So here simply now you can write the rate of mass transfer is equals to rate of reaction. So I can write Km and obviously your CAG minus CI, that is equals to Kr and Ci. So here it's very easy. Now you can calculate the value of Ci over here, Km into CAG minus Km into Ci, that is equals to Kr into Ci. So Ci you can easily find out, that is Km into CAG divided by Km plus Kr. Fine. So it can be written as also CAG divided by 1 plus Kr divided by Km. Fine. So just I have divided by Km on the numerator and the denominator both, and we will get this. You can get this kind of mathematical relation. Now we can find out the rate of reaction that is at the interface, that is equals to Kr into Ci. So we know the value of Kr that will be given in the problem, and we have calculated the concentration at the interface if the bulk phase concentration has been given, because it is very difficult to calculate the concentration at the interface. So it bulk phase concentration, or definitely you will be knowing these things. So you can substitute, that is CAG divided by 1 plus Kr by Km. Fine. So finally, what we will get, that rate of reaction at the interface, that is equals to obviously CAG upon 1 plus 1 by Kr plus 1 upon Km. So this is how the rate of reaction at the interface can be calculated, and one can calculate these things. Now, one major thing here is, here you can see the two resistance can work. One is mass transfer resistance, and one is your reaction is happening. So if let's say mass transfer coefficient is very high, so resistance is incurred by mass transfer. So which one is dominating? That is very important to understand over here. So I'll take two cases over here. First one is, if your Kr is very greater than Km. So if your Kr is very greater than Km, so in that condition, what you can say? So in that condition, you can say that 1 upon Kr is very less than 1 upon Km. So what I can say, 1 upon Km will tending to 0. So you can say 1 by Km will tending to 0. So here in that case, what will be the rate of reaction? Ra I, that is equals to what? CAG and divided by. So 1 by Km will be equals to 0. So it will be equals to 1 upon Kr. So directly you can write, that is Kr into CAG. Means if Kr is very greater than Km, so what happens? The resistance incurred by mass transfer will be, that will be very high, right? So 1 by Kr will be very less compared to 1 by Km, right? Sorry for that. Here I should write something else. Here in that condition, what is happening? Just try to understand. I am telling you, Kr is very greater than Km. So 1 by Kr, 1 by Kr will be very less than 1 upon Km, right? So 1 by Kr will tending to 0. I'll be neglecting that thing because comparative thing will be there. So the rate of reaction RAI, that will be equals to only Km into CAG. Fine. And in the second case, if I'm assuming Km is very greater than Kr, so I can write 1 upon Km is very less than 1 upon Kr. So what I can say, 1 by Km tending to 0. So in that condition, what happens? Rate of reaction minus of RAI, that is equals to Kr into Ci. So two different cases will occur when the rate of reactions, that depends upon the value of Kr and Km, and you can calculate the value of rate of reaction on the surface of the catalyst in that way. So obviously, let's say if Km is very high, so mass transfer coefficient is very high. Means whenever the reactant will be there in the bulk phase, what happens? It will immediately come to the surface of the catalyst and the reaction will take place, right? So if Km is very high, in that condition, what happens? 1 by Km will be very low, right? So resistance incurred by the mass transfer will be very low, and resistance incurred by the rate of reaction is very high, right? So obviously there that will be a reaction limited. And in second case, if your Kr is very, very, low compared to Km. So in that condition, what happens? Mass transfer limiting process will be there. So this is how this particular heterogeneous catalytic reaction system works when your catalyst surface is your non-porous, means catalyst is non-porous. Now I'll be talking about the next thing, that is when the catalyst is porous and how the mechanism works, how these particular things will react, how this reactant will come and get a job on the surface, and after that reaction will take place, and after that product will form. So in this gate has, I mean, if you'll see the syllabus of the gate has asked question. I mean, in the previous year they have asked questions on the basis of cylindrical catalyst only. So I'll be talking about only cylindrical catalyst, but based on that, the surface area will be different. If cylinder is there, then surface area of cylinder is different. If a sphere is there, then surface area of a sphere is different, right? So I'll be talking about the diffusion and reaction within cylindrical pore catalyst, right? Diffusion and reaction. So see, if we are having a cylindrical pore catalyst like that, right? If this one is a catalyst which is porous, earlier I have talked about the non-porous catalyst, right? So what happens? Your reactant is getting entered over here, let's say A, and having concentration here is CS, right? So reactant will get entered. So what happens, since reactant will be diffusing inside the pore of the catalyst also, and parallelly the reaction will be happening. So you can see the reaction is also happening parallelly, with the diffusion also. So let's say here at the pore mouth x is equals to 0, and at x is equals to at the rear end of the catalyst, right? So this is how this particular things work. So along x direction, if I'm talking about this one is your x direction, if I mean here I'm assuming that the diffusion is takes place in only one dimension, because one dimensional thing will be very easy to solve. So that's why I'm taking about the only one dimension, right? So in this cylindrical catalyst, what happens? The diffusion is taking place, and as well as the reaction is also happening. So let's say if I want to find out the concentration of the catalyst at any particular length of the at any particular end from the pore end. From the front end. So I'll take a small cross-sectional area element. Let's say I'll take a small cross-sectional area element having the thickness is dx, and here what happens? This one is your at x, and this point is your at x plus dx, right? So what happens here? Diffusion is happening, and as well as reaction is happening both. So if I'll apply the component balance, let's say since your A is diffusing inside the catalyst, pores of the catalyst, so I'll apply the component balance, and if the reaction is happening, let's say A is getting converted to R, having n of order of the reaction is 1 and rate constant is K, right? So if I'll apply the component balance, so what I can write, rate of A at Z or at X minus rate of A at X plus dx, right? This is your diffusion, right? And minus, obviously with diffusion reaction is also happening, so you'll have to take care of the reaction. So minus of Ra into dV, that is equals to 0. So obviously if you know this concept of chemical engineering we used to study, that is the basic concept of chemical engineering, in minus out plus generation minus consumption, that is equals to accumulation. But right now I'm talking about the steady state condition, so accumulation will be 0, right? So in, obviously this one is in, this one is out, and this one is your consumption. So generation for A is not getting generated because A is a reactant, so obviously it will be getting converted into product. So for A, you can write the consumption only. So this is what the thing that I'm writing over here in terms of in the condition of steady state. So we are assuming about the steady state condition only. So now, if you expand the Taylor series expansion of this particular thing, I'm not going to write everything directly. I'll be writing. So this will becomes dNA bar divided by dx, that is equals to minus of Ra into V. Right? Now, volume can be written as cross-sectional area, obviously cross-sectional area, and the thickness is dx. Fine? Thickness is dx. So obviously here there will be a dx term in multiplication. Fine? So now you can write minus dNA bar divided by dx into dx, that is equals to minus of Ra into V can be written as area of cross section into dx. Fine. And obviously Na bar can be written as area of cross section into diffusivity into dCA by dz, right? So if I'll substitute these things over here, so I can write minus, because this one is your fixed law of diffusion. Fixed law of diffusion will be valid. I am assuming here. So what I can write, if you'll substitute these things over here, so area of cross sectional, so you can write AC into D, and obviously D2CA by dx square, and dx will get cancelled out, that is equals to minus Ra into AC. Right, so this AC and AC will again get cancelled out. So what I can write is D2CA by dx square D2CA divided by dx square minus Ra in Ra, that is equals to 0. And what is minus of Ra? Minus of Ra is your KCA. Fine. If you will substitute these things, you can write D2CA by dx square minus KCA, that is equals to 0. So you can write D2CA by dx square minus K by D into CA, that is equals to 0. So this is your second order partial differential equation, or sorry, this one is your second order ordinary differential equation. So you can solve these things very easily, right? So let's say I'm assuming d square minus m square equals to 0, where m square is equals to K by D. So you can write m equals to root over K by D. Fine. So you can write D equals to plus minus m. The concentration Ca, which is a function of Z, can be written as C1 e to the power m1z plus C2 e to the power m2z. Fine. C1 e to the power m1z and C2 e to the power m2z, where m1 is equals to plus m and m2 equals to minus m. So directly I can also write Ca at z, that is equals to C1 e to the power obviously mz plus C2 e to the power minus mz. Fine. So this is the relation that you will be getting from here. Now the thing is that at x equals to 0, if you will apply boundary condition, what will happen? The concentration of the reactant Ca, that is equals to your Cas, and at x is equals to L, what happens? dCA by dx, that is equals to 0. Sorry, here it will be x, because I am assuming your dimension along variable is x, right? So these things you can write. So dCA by dx is equals to 0, right? So this one is your first boundary condition, this one is second boundary condition. Why? Because you are solving a second order ordinary differential equation, so you will require two boundary conditions to solve this particular differential equation, right? So once you will substitute this value at z equals to 0, let's say Ca is equals to Ca naught, sorry. Let's say I'm assuming Ca equals to 0, and at x equals to L, your dCA by dz equals to 0. So once you will substitute all these value, let's say first, if I'll substitute the first equation, so I'll be getting 0 equals to, no, sorry, I have assumed the concentration at the surface is your Cas. So you can write over here, after substituting first boundary condition, you can write Cas, that is equals to C1 plus C2. Let's say I'm assuming this one is equation third, and at x is equals to L, dCA by dx is equals to 0. So I'll have to calculate dCA by dx, that is equal to C1m e to the power mx minus C2m e to the power minus mx. Fine. So dCA by dx is equals to 0. So that is equals to, if I'll take common m, so C1 e to the power ml minus C2 e to the power minus ml. Fine. So from here you can get C1 e to the power ml, C1 e to the power ml minus C2 e to the power minus ml equals to 0. So from here you can get C1 equals to C2 into e to the power minus 2 ml, right? So earlier we have got a equation C1 plus earlier equation can be written as, let's say, C1 plus C2 equals to CAS. So you can substitute this value C2 into e to the power minus 2 ml plus C2 equals to CAS. Fine. So you can write C2 equals to CAS divided by 1 plus e to the power minus 2 ml. Right. So you have got the value of C2 over here. Now, from C2, you can get the value of C1. So C1 equals to C2 into e to the power minus 2 ml. So that is equals to CAS divided by 1 plus e to the power minus 2 ml multiplied with e to the power minus 2 ml. Is it clear? So you have got the value of C1, you have got the value of C2. So now the concentration Ca, which is a function of x, that is equal to C1 e to the power, obviously mx plus C2 e to the power minus mx. So C1 you have got, that is CAS divided by 1 plus e to the power minus 2 ml into e to the power minus 2 ml. Fine. Plus C2. C2 is your CAS divided by 1 plus e to the power minus 2 ml into e to the power, sorry, minus, here you can write like that, multiplied with e to the power minus 2 ml into e to the power minus mx, sorry, plus mx and e to the power minus mx. Fine. So finally, you can get CAS divided by 1 plus e to the power minus 2 ml common. So you can get e to the power, what? mx minus 2 ml plus e to the power minus mx. So if you will rearrange this particular thing over here, so you can get, that is CAS into, obviously, you can rearrange these things like that. It's very easy. E to the power ml upon e to the power ml plus e to the power minus ml, right? Into, obviously here CAS will be there. And again, you can multiply e to the power minus, sorry, mx minus 2 ml plus e to the power minus mx. Fine. So finally, you can write CAS and it will be equals to e to the power m x minus L, fine, plus e to the power m L minus x divided by e to the power ml plus e to the power minus ml, kind of that. Right. So ultimately, you can write this thing CA at x, that is equal to CAS into cos of hyperbolic m of L minus x divided by cos of hyperbolic ml. That's it. Fine. So this is the ultimate relation that you will be getting for a clinical port catalyst. So sometimes you will be asked about that, calculate the concentration of catalyst. Even if recently in 2022 or 23, GATE has asked a question on this particular concept, Ca by Cas, that is equal to cos hyperbolic m of L minus x divided by cos hyperbolic of ml. This is the desired equation that you are supposed to calculate. And here you can see Ca is a function of x, obviously, and m is equals to root over k by d, right? M equals to root over k by d. So if I'm talking about the graph of this particular thing, how this particular equation will look like, so it used to look like, if I'm talking about Ca of x divided by CAS, that is the surface concentration, and obviously it will be x by L. So it will look like this way. Let's say this is, the ratio can go maximum up to 1, and it will go like that. Right? So this will go like that. Fine. So here, if you will go from this side to this side, what happens? The value of m will be decreasing, right? So here m may be, let's say, 0.5, m may be 0.4, m may be 0.1, m equals to 0.05, kind of that. So m value will be decreasing. What does it mean? Means here, if m is decreasing, what does it mean? K is decreasing, diffusion is increasing, right? So in that particular region, what will happen? rate is less, diffusion is more. And in this region, what you can see? In this region, you can say rate is more and obviously diffusion is less. So based on rate and diffusion, you can identify that whether this is a reaction limited, whether this is a diffusion limited condition, right? So this is what the heterogeneous catalytic reaction work in case of cylindrical pore catalyst. In the next lecture, I'll be talking about some Thiele modulus concept and effectiveness of the cylindrical pore catalyst kind of thing reactions. Okay. Thank you all for watching the video.